Good evening, and I am super impressed that y'all made it up here on a cold night. But welcome to Kopernik Observatory. My name is Drew Desker. I'm the director here, and again, we usually do these Friday night programs. Well, from March to mid-December every Friday night, but in January, mostly because of it's cold, we sort of winnow it down to one, and you picked a good night to come up here tonight. By show of hands, who here is here for the first time or not since your fourth grade field trip? All right, a good portion of you, all right. Who here are members? All right, so a couple other people, there you go. So the people that raise their hand second actually have a sort of valuable piece of information. Kopernik membership not only gets you into Kopernik Observatory, but on Friday nights and other special events, but also we belong to what's called the ASTC, Association of Science and Technology Centers. And it's a consortium of over 380 other science centers that honor our membership card. So you could go to the Robertson Museum for free. You could go to the Ithaca Science Center for free, or the Science and Museum of Science and Technology up in Syracuse, or the Franklin Institute in Philly. The Corning Museum of Glass is also part of that, or the Intrepid Museum down in New York City that actually has the Enterprise, the space shuttle that they used as a sort of a test glider as they were ramping up to actually have this space shuttle program run. So if you sort of like this kind of place, consider getting a Kopernik membership, and you can go to our website and just sign up right online. We've been actually around for over 50 years. It was opened in 1974, a year after Copernic's 500th birthday, and that's what actually this place is named after, is the Polish astronomer Mikołaj Kopernik, who you more likely know as Nicholas Copernicus. Does anybody remember what Nicholas Copernicus was famous for? That's usually the answer. Yes. Exactly. He developed what's called the heliocentric model of the solar system. Up until Copernic's time, people thought that, again, all the planets and the sun all revolved around the Earth, but sometimes those planets as they were traveling, all of a sudden would start going backwards, and that bugged Copernik. Why would a planet turn around and go back? Sometimes even do it 2 or 3 times. So he did the math and determined if you put the sun in the center, it all made sense. So we are a public observatory, and it's actually, as a public observatory goes, we're actually probably one of the best cited and best resourced public observatories in the Northeast. There are others that might have one telescope, and it might be open maybe once a month or something like that. Very often they tend to be associated with universities that, they're basically they use their telescopes for their purposes. But we end up opening up every Friday night with these Friday night programs. During the school year, we do a lot of school programs. In fact, next week we'll have I think 3 days of schools coming up here to do school programs on a wide range of topics, not just astronomy. We also do summer camp programs. So if you've got a child that might be looking for or a grandchild that might be looking for some activity during the summer, we'll be announcing those probably in another month and a half. And these are week-long day camps. You can always go to our website to find out what's going on. We always point out our Friday night program. So tonight's program is on winter skies. Any of you educators out there, or even retired educators, if you're tired of sitting around, talk to us. Maybe there might be an opportunity for you to participate here. But one of the things that, again, I really enjoy doing are these Friday night programs. It's an opportunity for us to really expand our knowledge about a wide range of topics. Right now I'm in the process of signing up presenters that will start in March. And among the presenters we'll have is some people from Binghamton University, in particular one that has already signed up, who's doing some research on deep fake. How do you recognize deep fake videos? I don't know about you, but when I see, you look on social media now, the amount of stuff that just is absolutely crazy that you know is AI, but the question is the stuff that looks like it could be real, but is it? And so this BU professor will be talking about that. But again, these Friday night programs is an opportunity for us to continue to learn. I wish I could live another 50 years. I mean, when I grew up, I remember watching Neil Armstrong walking on the moon, and for people like as young as you, when I was your age, I used to have to walk to the TV to change the channel. You can't even find the button now to change the channel. You got to use the remote. So what's going to happen in the next 50 years? And hopefully we'll get a little bit of visibility into that. So what I'm going to do now is I'm going to just do a real quick shout out from a friend of ours, Dr. Michelle Thaler.
Well, hello everybody. This is Dr. Michelle Thaler from NASA's Goddard Space Flight Center, and all of you are in one of my favorite places in the world, Kopernik Observatory. I've been there several times, and I hope to get back sometime in the near future. I think you guys have some of the best tour guides for the universe there. I've been to many public observatories all around the world, and I have to say the staff and facilities at Kopernik are absolutely first rate. And the kind of work that's being done here is so important to us at NASA, because we can be out exploring the universe, doing everything that we do. And if that information doesn't get back to the public, if somebody doesn't make you care about that and feel like you're somehow involved in what we do, then really we're wasting our time. And that's the great work that the people at Kopernik Observatory do. I think they really get you involved, they really get you excited about what we're learning about the universe. So I hope you have a great visit. Again, thanks for coming, and I hope to see all of you soon when I get back to Kopernik Observatory.
The one final thing I'll mention is that all of our Friday night programs are live streamed. So I want to welcome those watching on the live stream right now. But if you go to our YouTube channel, you can actually look at what we've done in the past for literally the last 5+ years. Back in the fall, we had a talk about Easter Island, or we had a talk about the Panatel. Of course, there's always talks about various aspects of astronomy, but we even talked about what's causing butterfly decline. And the Galapagos Islands. So check it out. If you're not able to come up on a Friday night, you can actually watch live, and you can ask questions through the chat. Or if you want to even watch tonight's program tomorrow, to remind yourself of what Jenny showed, you can do that as well. So again, we're very fortunate to have some great staff, and one of which is our live streaming astronomer, Jenny Carty, who is going to do her talk on winter skies. So I'm going to turn this over to Jenny, and we'll get you on your...
All right, so I think my mic's going. Test, test. All right. So hello, everyone. Welcome to Kopernik Observatory, and as Drew mentioned, awesome that you made it up our hill, especially before this big storm hits. And I guess very appropriate that we're doing winter skies this Friday. So yeah, the Winter Skies program, it's an introduction, or any of our skies program, because we do this every season. It's an introduction to astronomy. So you're going to get a little background on how we navigate the sky and how we characterize it. And then we'll get into what's visible in the night sky this time of year. So let's head through. So this is our overview. We have the ABCs of stargazing. What can we see in the sky? And finally, some observing tools you can use, whether you're up at Kopernik or you are at home and you have some, even in town areas, even in some city areas, your options aren't diminished at least for the bright objects. The moons, planets, planets, those are all options for you even in brighter conditions with light pollution. The advantage of coming to places like Kopernik is more of the sky opens up to you. More objects, the dimmer objects like galaxies and nebulae, so much to explore with those. So our dark skies are great for that. So the ABCs of stargazing, starting with A. A is for angular size and distance. And here is the tool that you can use to measure your distances of objects across the sky. You have it right on you. It's a handy tool. And we can practice this right now. What's not listed up here is how far away your hand should be to make this work. Because if it's this close to your eye, that's a big difference from this far away, right? Ooh, getting some feedback. So with our pinky, stretched at arm's length, the width of your pinky is 1 degree across. So what's also interesting about this, your pinky nail, this may surprise you, your pinky nail at arm's length is the size of the moon in the sky. And while the moon is the most conspicuous and biggest object, the moon and the sun are about the same, but the moon looks very large in the sky, but that's because there aren't a lot of bright, large objects in the sky. So compared to everything else, it's pretty large, but even still, it doesn't take up that much of the sky. Another fun fact, if you've ever wondered, why does the moon look bigger when it's near the horizon? Try this. It will be the same size, no matter where it is in the sky. It's an optical illusion. So that's one way to prove it. Arm's length, measure it on the horizon, and when it climbs up in the sky, measure it again, and you'll see it's the exact same size. All right, then 3 fingers together, arm's length, that's 5 degrees across. If you make a fist, the width of your fist at arm's length is 10 degrees. And while I'm not a fan of football and things, my family would not be happy if I didn't say, hook 'em horns. So at your fingers spread, your index and your pinky, that's 15 degrees across. Now, you do have to kind of get this right. You can't really super extend your pinky out. But then again, it's just an estimate. So just a slight spread there. And then one great object to try this with is the Big Dipper. It's a very conspicuous object in the sky, a constellation in the sky. And you can measure, and if anyone wants to take their phone out and take a picture of this slide, feel free. This will also be on YouTube, so you can always go back there as well. But this is a great way, because you'll find the Big Dipper right in the north of the sky, and you can start measuring the stars. So 25 degrees from the furthest point of the tail to the corner of the cup of the Big Dipper. So this is how we can start measuring objects in the sky, just roughly. How far is that star from the horizon to where it is in the sky? When you're measuring that, you're measuring an altitude. So you can practice that. And what's cool, you can also stack. At arm's length, you can just go 10, 20, 30, 40, and climb up towards zenith in the sky. So we're able to measure degrees between objects, and it's also handy for talking and communicating with each other where these objects are at any instant in time. Because you may have noticed, if you ever pointed something out in the sky, in a nice, clear, dark sky, you're like, it's right there. And the person next to you goes, what are you pointing at? That's parallax. So we need some way to define what we're looking at and where we're looking at it. B is for brightness, and in astronomy we call this magnitude. So how bright objects are, that's one other characterization we have to make, and it's a big range. Here's our number line, and I think you'll notice something immediately about this number line. What's weird about it? Any thoughts? What do you notice?
Objects are more negative.
Yeah, so we have the sun, the brightest object in the sky, all the way here on the left side of the number line in the negatives. And then if you know some objects out there, and even says things like faintest naked eye objects, very faint, that's out at the positives. So this is inverse to how you would think about something being bright should be a big number, right? The reason for that, astronomy is a very old subject matter and a very old science. So early on, when astronomers were trying to categorize objects in the sky in terms of brightness, specifically categorizing stars, they would classify them numerically in a rank. So your brightest stars get the rank of number 1. Your dimmest stars go out there at number 6. So it was ranked before, and then over time we modified this ranking system into this number line you see today, and we've placed the sun all the way at the end of it out towards -30. So it's not very intuitive, but that's the problem of being a very old science. It's just there's a lot of legacy, and things just didn't change. So the sun is way on the left side, and if we come down, the next brightest object we see in the sky is the full moon, and that's out there near -13. Continuing down this line, we have Jupiter, one of the brightest planets. Jupiter and Venus. Venus can get brighter than Jupiter, but they're usually pretty close. So right out here towards -3. And a good 0 point is the star Vega. Anyone seen or read Contact? It's a really good book. So that's the star that they hear a signal from. It's pretty cool. Now, not in real life. It is fiction, but that is Vega, a nice bright star in the sky. And then moving past the 0 point, you can get out to some galaxies. Now notice, Andromeda Galaxy is before our faintest object that our eyes can see. So that means you can see a galaxy with your own eye. In nice dark conditions, no moon in the sky, Andromeda is pretty apparent. And while conditions might not be ideal tonight to view Andromeda, I do recommend you go hunting for it in dark skies when you have the chance in the winter time here, ideally within the next month, because it's going to start getting close to the western sky starting in February. So be on the lookout for Andromeda. It looks like a cloud, and if I recall, I think if you could see it, which you can't see the entire thing with your eye, you can only see the brightest parts. But if we could see Andromeda in the sky fully, it would be 3 moons across. It's a really big object in the sky. So then we get to our 6. Magnitude 6 is about where we stop seeing things. And again, this is in the darkest of skies. So light pollution affects all of this, of course, too. But in the darkest skies, we can see out towards 6. And then beyond that, we need tools. We need telescopes, binoculars, cameras to see the objects beyond. So that's out where we have our very faint. So that's brightness or magnitude, another major component in characterization of astronomy. All right, C is for coordinates, and I'm going to teach you 2 coordinate systems today. We already learned a little bit about coordinates with our angular distance. You already started that process of measuring the sky. And you did that with altitude azimuth coordinates. So you're an observer, and at your observing location, you can look around the compass directions. And these are mapped just like you'd expect. North is our 0 degrees, east is 90, south is 180, and west is 270, and then back to our 0. So that's your azimuth. Azimuth is your rotation around you, compass directions. And then you have your altitude. And that's just your climb from horizon to the peak of the sky. So your horizon is 0 degrees, and you climb up to zenith at the top of the sky, and that's 90 degrees. So altitude only goes to 90. That's your zenith marker. All right, so let's say you go looking for a star in the sky, this one over here, and you measure out. You have your compass with you. You're going to measure with your compass. Go around, past east, not quite to south. That's an azimuth of 150 degrees. And then you measure your altitude, climb up in the sky. That altitude is 50 degrees. That's the location of the star you've observed. Then we have the North Star. Now, the North Star is only visible to us in the northern hemisphere. Once you cross the equator into the southern hemisphere, you won't see the North Star, nor will you see a South Star. There's no bright, conspicuous star for the southern hemisphere that points due south, at least right now. Over thousands of years, this does change. We'll lose the North Star one day, not in our lifetime, but one day the North Star will move on, and that's really because the Earth rotation is precessing. And in the southern hemisphere, maybe one day a bright star comes along as the Earth precesses. So it's kind of cool to think about that, though, that someday we won't have the North Star in the sky. Well, pointing due north. All right. So then we climb up, though, to find the North Star. It's at the due north marker. So don't stray from the due north. Then you climb up into the sky, and the altitude is your latitude. Does anyone know our latitude here in our area? 42, yep. 42 degrees is our latitude. So it's another convenient way. If you just end up lost somewhere, you can get your latitude at least if you find the North Star. And the North Star is found at the tail end of the Little Dipper. I'll show you how to find that when we use a tool called Stellarium. All right, it's equatorial coordinates. So altitude azimuth coordinates are great for a single instance in time. So you're an observer at a specific location. Maybe you have other people around you. You're trying to communicate where things are in the sky. That's perfect. We need a coordinate system, though, that has defined points, but defined coordinates for objects. We need to map the coordinates to a star field, because at any instant with altitude azimuth, let's just say it's the North Star is going to stay where it is, but that other star, let me just go back to that slide for a second. This other star, as Earth rotates, this star is going to move across the sky. It rises and it will set in the western sky. So what we need to do, because its alt-az is changing, we need to find a way to build a coordinate system that gives that star a unique coordinate that doesn't change over a long period of time. So we do this in a pretty clever way. So I have 3 globes up here. The first globe is your standard globe of the Earth. We can spin the Earth, and we know our equator. That's going to be important. This globe is not of the Earth. It's a globe of space. We call this the celestial sphere. The celestial sphere is a projection. It's our view of the sky from Earth. And so it's this shell around us. This was actually an early model of how people looked at the universe and how they understood it. They thought of it as a shell around our planet of stars. And they were all fixed to that sphere out there, somewhere beyond us. We can still use this model. It's only good as an observational model. It's not a real 3D model of the universe. We now know the universe is expansive, and all of these objects out here are located at different 3D coordinates. So that's a whole other thing. But for astronomy's sake, for telescope use, we can still use this model of the celestial sphere as a map to the sky. So we start with Earth here, the globe of the Earth at the center. Oh, and that's what this one is. I will come down later and show you this up close. Earth is at the center, and then the celestial sphere is around it. So as we piece this together, keep thinking about this in 3D. 2 spheres, Earth and celestial. All right, so let's start building it. First thing we got to do is we take the Earth's equator and we send it out into space. It's 1-to-1. We're pushing the Earth's equator out into space. Similarly, we take Earth's latitude lines and send those out into space to the celestial sphere. And we call this system here declination. It's kind of like altitude in a way. That's the most analogous we can make it, but these lines here are our declination coordinates, like sending latitude out into space from Earth. And now, through this sphere, we have the path of the sun, the apparent path of the sun. Now, what drives this is the Earth going around the sun. But we can still model it as if the sun is going around the Earth in this celestial sphere. So that's what this green path is, the path of the sun throughout the year. We call that the ecliptic. The ecliptic is the path of the sun. And from this, we can build our next coordinate system. That is the right ascension. So declination is like latitude. Right ascension, which are measured in hours, is similar to longitude. But here, instead of the prime meridian, how we define the start of right ascension is, here's our 0 degrees. This 0 degree marker is the vernal equinox, the spring equinox. So that's coming up soon. I think I'm looking forward to that. I don't know about you. But yeah, in March, we'll have the vernal equinox. And that's when the sun crosses this path. So we count that as the 0 marker for right ascension. So 0 hour, 1 hour, go all the way around 23 hour, and then mark it, just like hours on a clock. This is a 24-hour clock, though. All right, so there's your right ascension. Now things are getting crazy. You can see building this coordinate system, it gets messy. But what we just mapped in here, we've added some labels. So marking, we have celestial equator, we have our ecliptic, we have vernal equinox, and we've also added the constellations to mark out where their placement. And in the celestial sphere, there are 88 constellations total. For us here in the northern hemisphere, we only get to see about half, a little bit more than half throughout the year. And if you cross over the equator into the southern hemisphere, that's how you see the other half. Because the Earth itself blocks us from seeing We're a sphere, so we don't get to see constellations down here when we live in the northern hemisphere. All right, so let me come just around to show you this 3D model, because this can help a little bit to understand that coordinate system a little better. So I'll come around, show you again, the Earth is at the center, and then around it is the celestial sphere, and you'll see those constellations marked around it as well. Woo. That spooked me. All right, so our equatorial and alt-azimuth system. So again, one more time, alt-az, you're observing from the ground, it's your point, and it's an instant in time is what you're measuring. Equatorial is longer term. It gives unique coordinates to stars, especially in the sky. And this is the coordinate system most telescopes will use, especially most high-end telescopes, because it keeps up with the rotation of the Earth. Each one of our telescopes out at the observatory uses an equatorial mount so that it can track objects easily across the sky. We have it synced up to, let's say, Vega, like we saw earlier. We sync it up to Vega, the telescope will stay right on top of it throughout the night because of that equatorial mount. Alt-azimuth mounts don't work as well at that. So if you're looking for a telescope, while they're more challenging to use, consider an equatorial. All right, now I want to show you this application called Stellarium. So if you just go to Stellarium, that's stellarium.org. There's all, for every operating system you could think of. You can download it for Linux, Mac, Windows. You can also download mobile apps for Android and iOS. And then there is a web-based version if you just want to run it in a browser. And that's what we'll do today, because it is the simpler version. There's less to learn in this version of Stellarium. As you advance, I recommend downloading the more advanced one, though. All right, so Stellarium is your at-home planetarium. It lets you move across the sky. It still says we're unknown, so I'm just going to make sure that we're not at 0, 0. 0 latitude, 0 longitude. That's not helpful. Oh, it finally found us. Well, maybe. That's still not quite right. Oh, actually, no, it is. Never mind. All right, I think we're close enough. 42. No, yeah, it says 44, doesn't it? Why didn't Vestal come up? Come on, let's try again. Come on. Is the internet not working? Let's try that. Okay, let's refresh. Well, maybe I can't show you the web one. I might have to go back to our downloaded version. I will load it in the background while this figures itself out. There we are. Okay, we're in Vestal now. That's all I care about. So Stellarium's your at-home planetarium, and we can click and drag across the sky to move around your compass directions. Remember, this is your azimuth, and we can look up and down in altitude, and we can see the entire sky at once. Or you can zoom in and get a closer field of view to what you would see across the sky. is misbehaving today. I wonder, I was having trouble with it on my laptop earlier too. I wonder if they need to work on this. It's been stable in the past. Make sure one more time that we're where we need to be. Nope, it really likes Waldeboro for some reason. All right, I'm giving you one more chance, web version, and then we're going to move on to the other one. All right, so we look around, and if we look to the western sky, you'll see Saturn and the moon are out tonight. We climb up higher in the sky, we come by Orion. There's the constellation Orion. And here's Jupiter in the sky. Now what's also great too is we can map out our constellations. Just like that, we connect the dots. And we draw some constellation artwork too. You are interested in the mythology. All right, you can center in on objects. This isn't working today either. I think they broke their own app. All right, I'm giving up on the web version. Maybe you'll have a better success at home. You'll see what I mean. When we load the downloadable version, there's endless features in here. You could spend hours exploring this version of the app. Well, days, weeks. All right, here we go. I'm just gonna pop back over and because I can hear our computer chugging now. I'm gonna close out of this. We don't need to run 2 instances. Okay. So similar though, you have these toolbars here. We can map our constellations. And if we click on an object, you get context about it. So up in the upper left, that's what was supposed to happen in the web version. But in the upper left, you can see it lists magnitude. So you can actually measure the brightness of these objects at a given time. So Jupiter is at negative 2.65 tonight. So like we saw in the number line, closer to -3. All right, now another cool thing is we hit the space bar to center in, and we can zoom, zoom, zoom using the scroll wheel and get a telescopic view of the objects in Stellarium. And it looks like tonight it does match the true rotation period of Jupiter, so the Great Red Spot would be visible tonight near the edge of it. And Jupiter has a particularly fast rotation period, about 9 hours. So even just using the clock on Stellarium, you can click ahead by just 1 hour and see the Great Red Spot rotate. And we can return to current time like that using this little hourglass feature. You can also smoothly fast forward or rewind through time. Oh, I clicked off of it. Bye, Jupiter. Okay, we will return here. All right, now we can do similar with Saturn. Hit the space bar and zoom in, and we'll see Saturn's beautiful rings and its moons all in a nice line, orbiting around. So both with Jupiter and Saturn, we can see its moons when observing. We'll come back to this though, because what I want to show you briefly here in Stellarium is the systems, the equatorial and azimuth coordinates that you can map on to the celestial sphere. So here's your equatorial, and if we pan around, you'll see the North Star lines up at the very tippy top of our celestial sphere. this is your 90 degrees declination. And that means the north pole of the celestial sphere lines up with the north pole of the Earth. Same with the south poles. You can see how the Polaris is just a little askew. It's not perfectly aligned with the north pole of the celestial sphere. So over the course of the night, Polaris does spin around this central point. You won't notice it by eye, but it's not a perfect North Star, kind of like we talked about earlier. It is at the tail end of the Little Dipper here. I'll turn the map off for now, the coordinates off, because I want to show you the Big Dipper here. This is the best way to find it. The Big Dipper is nice and bright. If you take these two stars in the Big Dipper, they draw a line out to the North Star. North Star it's visible to the eye, but it's not super bright. It blends in with a lot of other stars, and then the Little Dipper is pretty dim overall. So look for the Big Dipper instead and use that trick. All right, let's hop back to this. Yeah, that's good. All right, so now getting into what we can see in the sky this winter. Firstly, we can see the International Space Station. So the ISS, there are two space stations in orbit around Earth, and this is low Earth orbit. There are two stations, the ISS and Tiangong Station from China. The ISS is international with collaborators from the US, the European Space Agency, JAXA, which is the Japanese Space Agency, and Russia as well. So it is a collaborative effort that took several years to build in its full capacity, and it's been mission-driven for the last couple of decades now. They are decommissioning it in 2030. It will come back down to Earth at the end of 2030, maybe early 2031. Don't worry, it's not going to fall on your house. They're guiding it back home. Yes. But that's because space stations do have a shelf life. They micrometeors penetrate them, which sounds scary, but there's it has a threshold where it becomes dangerous. So they're starting to experience some minor leaks, and it's just a matter of human safety. You want your astronauts to be safe when they're orbiting above the Earth. So ISS orbits just under 250 miles above the Earth, and it does so once every 90 minutes. This thing is just zooming around our planet at a speed of 17,500 miles per hour. And little context there, at that speed, you could travel from New York to LA in less than 9 minutes. So this thing is really moving fast. And you can see it when it goes across the sky. It's moving over the course of a few minutes from horizon to horizon, or from starting point to end point. It's pretty quick. So here are some ISS flyovers coming up. There actually was one. If the conditions were better, we could have gone out beforehand, before the talk, to see this fairly bright one, which started at 6:56 and ended at 6:58. Now, why does it not make it very far across the sky? Because eventually the ISS, depending on its trajectory, the only reason we're able to see it at all is those big solar panels in the station itself are reflecting a ton of sunlight. It's so high up that it hasn't experienced sunset yet, like we have. So it reflects the sun back down to us, but eventually it will cross over into the Earth's shadow. And when it does that, it disappears. So that's why it doesn't make it very far across the sky, only 10 degrees altitude to 21 degrees, northwest to north. Tomorrow has a couple of chances, and this is a fairly bright one. This is a much dimmer one, and also pretty short. I think it's less than a minute in its entirety. So maybe target this one. Starting at 6:08 p.m. northwest, altitude of 10 degrees. It'll climb up to 20 as 6:11, and then fades away at 612 at an altitude of 16. So doesn't get super high up. Sometimes it will. If you want to take, there are apps for this where you can track the ISS. Stellarium will actually show you where the ISS is as well. But one recommendation also is heavensabove.org, or sorry, .com, heavens-above.com. And if you click ISS, they also have Tiangong Space Station. You can see, we have these first three here. But you can see all the opportunities to spot the ISS. It looks like, oh yeah, there's a really good one, January 28th. Very bright, it's brighter than Jupiter. Starts at 6:09, highest point 71 degrees at 6:12, and then disappears at 6:15. So try that one out too. That one's going to be a better opportunity. All right. Now you may ask too, okay, we got the ISS, we got Tiangong Space Station. Who is in space? That's literally what this website is called. It tracks who is in space at any time. Whoisinspace.com. There are 6 humans in space. Here on ISS Soyuz mission MS-28, this launched November 27th of last year. We have 1 American astronaut and 2 Russian cosmonauts. Now, the ISS is kind of in a weird place right now. You may have seen in the news that they had to stop the Crew 11, right? Crew 11, Drew? Yes. I think Crew 11. They had to, yeah, they had to cut that one short because one of the astronauts on board had a medical condition that came up while they were in space. So they had to come back. The astronauts in stable condition from what NASA has shared. So they don't mess around with astronauts' lives. That's what you will see. And similarly, when they had the issue of sending the Boeing spacecraft up there, NASA did not feel like after the travel there that it was safe to take astronauts back home. This was over a year ago now. And so astronauts had to be there for months and months because they don't want to risk their lives. All right, so that means there's only 3. This number can fluctuate. Sometimes it's as high as 11 because they also send commercial flights up there nowadays for quick trips. And then Tiangong Space Station has 3 astronauts as well. Now, it's too bad, I'm just realizing, I'm connecting some dots here, and if like Artemis launches, Artemis 2, which is the crewed mission to orbit the moon, because Crew 11 had to come back early, I don't think we'll see like this really high number. It's just too bad, because that would have been a cool opportunity to have the ISS is stacked up with people in there. Then you have Artemis 2 orbiting the moon. This number would be pretty big if the missions went as planned. But sadly, if Artemis 2 launches when it's supposed to, the next crewed mission probably won't be on the ISS. Even still, we're going back to the moon. That's pretty exciting. All right. So whoisinspace.com, great resource. Now the solar system. First, the sun. Now, this is the big one. Don't view the sun without the right equipment. Basically, at Kopernik Observatory, we'd be happy to show you the sun during the day, during programs where we allow it. We have the right equipment to make that safe. We have special filters that remove well over 90% of the sun's light and remove all its harmful rays, like its ultraviolet. So when you do that, you see surface features on the sun, like these sunspots. Those are storms that happen on the sun, magnetic storms. And solar maximum occurred, I think they said, it was between 2024 and 25. And I think the original thought was it was going to be July of 25, but it ended up being a little bit earlier. And that's when the count of these sunspots is at its highest point, the most storms happening on the sun. And so we're moving away from that, but even still, we're in this kind of peak of activity. And then what that means is that if those storms are big enough, they can cause some pretty dramatic northern lights displays. Now, northern lights are always happening up north and south pole, but during solar maximum, the northern lights come down south to our latitude or even below. And this was the display of northern lights in October of 2024. Big storm happened that day, and there's actually so much interesting stuff happening in this display of northern lights. It happened, oh no, this was the August one, I'm sorry. We had two of them, August 24 and then October. And if you look carefully, there's a single frame in here with a bright streak in the sky. Very quick. That is a Perseid meteor flying through the sky. So we had northern lights, we had Perseid meteors, and then also we had an exploded rocket. All these pieces that are flying through the sky there, they resembled satellites, but they were all over the place. But what that tells you is that something probably exploded, and it did. We found out that a rocket exploded in the upper atmosphere. So there was all this shrapnel in space. Not probably what you want, but that's what we were seeing. So an interesting effect there too. Meteor shower, rocket pieces, and the northern lights, a beautiful display. And if you want to be up to date on the northern lights, there actually was an opportunity, or we were hoping there'd be a really good opportunity over the last week when a huge storm came from one of the sunspots and made it to Earth. Unfortunately, it more favored Europe than it did the US at the time, but there are some pretty amazing pictures from those northern lights. And I know some people in our area did catch the spikes of it for us and got to take some images. I saw some from Ithaca, from Rochester, a little further north from us. So spaceweather.com. By the way, that image we just saw of the sun was today's image of the sun. So you will see live images of its current conditions. And then down here, you can track its current status. They will give you a blurb. So saying the sunspot number is high, that means storms could happen. And then down here, go to more data, and we can see the activity. For us, on this chart, we would want to see something in the orange or ideally the red. But orange, we might just eke out some visible aurora for us. So right now it's quieter. All right, spaceweather.com, another wonderful resource for you. Just be on the lookout for maybe a couple more chances of northern lights. Eventually it will quiet down and we'll lose our chance for about 8 years or so. But now's the time to be on the lookout. Okay, the moon as well, and this is about tonight's moon, a nice waxing crescent. And one lunar cycle is 29.5 days, so that's how long it takes for it to go through one complete cycle from new moon to full moon and back to new moon. That's one cycle. And how to observe? Well, the moon is bright, and through our telescopes, you may notice when you look at it, it's really bright and very dramatic, and you may feel like you may have gone blind in that eye because it's dark out after you look. The moon's light is not going to hurt you. It's reflected sunlight. It is much dimmer than the sun. We saw it on that chart where it fell. It's not going to hurt your eyes. It's just a particularly bright object. So sometimes we use moon filters to knock that down a bit, make it more comfortable, but it's not going to hurt you. So unaided eye, binoculars, telescopes, cameras, it's all fair game for the moon, unlike the sun. Now, on March 3rd, there is a total lunar eclipse. So technically still the winter, heading towards spring though. This photo was from last year's, I should say 2025. This photo is from last year's Pi Day total lunar eclipse. And This was taken on our 6-inch refractor telescope here at Kopernik. And I can show you a little bit about total lunar eclipses. You can think of them as the opposite event to a solar eclipse. Solar eclipses happen only during a new moon, so that's when the moon is over here, and everything lines up just right so that the moon is able to block out some or all of the sun and projects its shadow down onto Earth, on the daylit side of Earth. A total lunar eclipse is this event, where you have sunlight casting on the Earth, but the Earth is a solid body, so it casts a shadow. And when the moon enters that shadow, you have a lunar eclipse. A total lunar eclipse is when it fully enters that shadow. There's two parts of it, and if you look at the shadows in the room right where you are, you'll notice these two parts of a shadow: a penumbra, which is a more diffuse, dim shadow, and then the umbra, which is a very dark, sharp shadow. So the penumbral eclipse isn't as noticeable when it starts there. Once you get into the umbra, that's where you really start noticing the effect of the eclipse. All right, now lunar eclipse here, just showing you as it moves around, the alignment has to be just right for these events to happen, especially solar eclipse, but lunar eclipse as well. So you can't have the moon too high or too low, it has to be just right. Here is the breakdown for the total lunar eclipse on March 3rd. This is where it's not so great. You're probably seeing the times and like, oh. So March 3rd, starting at 3:44 a.m. There's 7 stages to this total eclipse. The penumbral eclipse starts at 3:44, partial eclipse at 4:50. I would say you would really want to see the moon because this is when it turns red. At 6:04, so that's not too bad. If you wake up early, 6:04, yeah, you can catch the red moon. And maximum eclipse is at 6:33. At that point, it is going to be very close to the horizon, so you don't want any trees around you to see maximum eclipse. Shortly after, the moon sets, so we don't actually get to close out the event here at our location. It will continue, but the moon has set, so we don't get to see it. All right, so that's the breakdown. If you want to learn more about this eclipse event, check out timeanddate.com. They have all sorts of events there, including solar eclipses, if you want to look into those. All right, planets. What 2 planets do we have out? We have Saturn and we have Jupiter. This is a little animation here of Saturn that we took on our 6-inch refractor, the Orion telescope, back in the fall. If you look carefully, if it plays again, well, maybe it won't, but there was a little shadow that moved across the top of the planets. That shadow was Titan, Saturn's moon Titan. We won't get to see that transit event for a few decades, but Jupiter, it happens more often. So Jupiter, we see its moons transit. So this is Io, Jupiter's moon Io there. You can just about see that circle of the moon, and then its shadow. And we can connect these back to eclipses. These are solar eclipse events happening on the gas giants. So while you can't stand on a gas giant, if you were around that zone, you would be in the shadow of one of the planet's moons. And we saw those two in Stellarium. Saturn you're going to want to catch first when you go out to observe. We're not going to have too much more time with Saturn. As we head into the spring, it's going to get closer and closer to the sun. It will start setting earlier and earlier, and then we'll lose it for a bit. Once it crosses the sun's disk, as we orbit and as it orbits, then it'll become a morning object. That should start happening, I think, in the late summer is likely. So then we have to wait for it all to happen again. Jupiter we have for more time. We'll see Jupiter into the early summer. All right. We did do that earlier, so I'm going to move forward to the deep sky objects. So deep sky objects. These are objects that are pretty dim to the eye. Telescopes help. This one in particular is pretty impressive through a telescope. This is the Orion Nebula in the constellation Orion. And with a lot of these deep sky objects, you'll see these categorization numbers. The Orion Nebula has M42 as its catalog number. The M stands for Messier, and the 42 is just the number of this object in that catalog. Messier, Charles Messier, was an astronomer, and before we knew what all these objects were, he built this catalog to tell us, okay, these are not comets. He was tired of people coming to him and saying, is this a comet? I found something in the sky. Is this a comet? It's not a comet. I don't want to deal with this anymore. So he couldn't tell us what it was. Science hadn't advanced enough to that point. But he built this catalog to keep track of the objects and to confirm they weren't comets. So the Orion Nebula is a star-forming region in space. These are baby stars in here at the center of the funnel. This area here is called the trapezium. And the pink color is indicative of hydrogen. Hydrogen has this pink glow to it when it's energized, and hydrogen is star stuff. It's what stars are made of. When hydrogen gets super close and compressed together, the hydrogen starts going through fusion. Usually they'd avoid each other, but they're so squeezed together that they can't help but collide and combine and create helium. That process is very energy intensive, and that's how stars ignite and exist and burn for millions and billions of years. So that's a nebula, star-forming region in space. Now, after a nebula runs out of fuel, the stars start spreading out into space and making their own solar systems, and this is the effect. This is an open star cluster. This was taken by one of our Astronomical Society members, George Normandin, and this is the Pleiades open star cluster. So you can still see some nebulosity. Not enough gas to start forming stars anymore, but there's still a lot of remnants from the nebula that once existed there. This is M45, not Comet 45. And one last fun fact about Pleiades. It may look a little similar to you, and in Japan, this object is known as Subaru, and that is what makes a Subaru a Subaru. The logo of Subaru is based on this object in the sky. All right. Andromeda Galaxy. I mentioned this one earlier. Very large galaxy in the sky, M31, and visible to the eye, especially its bright core. Every spiral galaxy like this, including our own Milky Way, has a supermassive black hole at its center. But black holes are not cosmic space vacuums. This is evidence for that. It's not just sucking in all the light and matter there. Things are very close together and orbiting around that black hole at the center of the galaxy. That's why it's so bright and energy intensive. So, big object to look at in the sky and visible to the eye. So we can go hunting for these in Stellarium. Bounce over here. We can show you the search function. All right. So we'll start with Orion Nebula. And you can scroll down here to find it. It's actually a pretty conspicuous object. You will see evidence for it in this in the constellation Orion. But this is the constellation Orion. You have two shoulders here, two bright stars making the shoulders. Orion's, if we put the artwork on, you'll see it's Orion's right shoulder. Okay. So Orion's right shoulder is called Betelgeuse. Don't say it 3 times. And Betelgeuse is a super red giant star on the verge of going supernova. Now, it's likely we won't see that in our lifetime. We want to. It'd be very exciting. But when we say on the verge, it could mean today. It could mean 10,000 years from now. We don't know. If it does explode, it would be visible in the daytime sky. It'd be so bright. So that's why we want to see it, right?
How long will it last, probably, when it happens?
It does dim pretty quickly. It will dim over the course of maybe a decade or so, but it'll still be a bright telescope object once it happens for many, many years to come. So there's evidence for supernova being observed in the sky over the course of human history. And the reason we know they're visible in the daytime is because those recordings happen. They're like, wait, that thing wasn't there before, and now it's there. And we now know those were supernovae happening in our galaxy. Thankfully, generally, supernovae are not something you want to happen close to you, but Betelgeuse is really far away, so we're safe. And it's really the only one that's super close to going supernova that's near us. All right, now back to the Orion Nebula. You probably have seen these 3 stars in a line this time of year. That's Orion's belts. And if we scroll in, zoom in, we will see a nice depiction of the Orion Nebula right in Stellarium. And the stars at the center are all depicted, the trapezium at the center. It's very much shaped like a funnel in 3D space. All right. Now actually right close by, it's not as bright. In fact, this is a dark nebula, we would call it. Because the only reason you can really see it is because there's a nice backdrop of hydrogen glow. This is the Horsehead Nebula. I'm sure you've seen pictures from Hubble of this object. And that's what these nebulas get their names from, often from what they look like. This is kind of like a horse heads peeking out in space. That's right nearby too. Thankfully, the luminosity of that background nebula is pretty bright. So while you can't quite see it that well with the eye in a telescope, cameras pick this object up really nicely. Same with the Orion Nebula. Cameras are your best friend when it comes to observing, because they just do a better job at seeing these things and seeing color. All right, let's go to Pleiades, which is right nearby. I don't even need to use the search function. In Taurus the Bull, we can zoom in, and there is Pleiades, the 7 sisters. So that open star cluster of young stars spreading out into space. And then finally, we have Andromeda. And Andromeda is going to be setting in the western sky. As I said, our skies get darker still this time of year, so we can start observing earlier. That'd be the benefit of looking for Andromeda in that case. Start as soon as the skies get nice and dark. So here's the Andromeda galaxy. So you could really go hunting for these deep sky objects. There is a toggle here. And you can see these little circles that popped up are our deep sky objects that you can look around for in Stellarium. These things are dim enough, a lot of them are dim enough that you really can't target them by eye. This is where those coordinate systems become very important. All right, back here. Now we're going to start closing out here, but before we do, I have some tools you can use. We've already talked about a few of them, including Stellarium. So there's that website, stellarium.org. The web version, the iOS and Android apps are really good, so in the downloadable version. Stellarium is free, that's the other advantage. These also have free versions, but these are applications that you can get on your smartphone. So Starwalk and SkyGuide are very similar in skill level. They're basically just aesthetic choices and how they represent data and things rising and setting, and the notification systems are different. So you can set up a notification on these to tell you when something's rising or setting. So they're very similar though, just kind of choose your favorite. And then Sky Safari is a more advanced application for your phone, and also you can get it on desktops and laptops. And it's the same base idea of a planetarium on your phone, but it has so much more information and really advanced features as well. You can control telescopes using Sky Safari. If you have the right gear, you can control your scope. You can also set up configurations if you want to get into astrophotography, or if you like astrophotography already. You can set up telling Sky Safari, what's my scope, what's my camera, and it will give you a field of view, a box, mapping out your object in the sky. So you can figure out, okay, does my camera and my scope, does this work? Can I frame this right and how I want it at a given time? Really useful stuff. So Sky Safari at that advanced level is a paid app, but well worth it if you're into astronomy. Now, we have apps for our smartphone, but wouldn't you know, you can image the sky with your smartphone. So I really recommend trying that. You can do some Milky Way photography with modern smartphones. You can take pictures of eclipses. This is last year's, that picture from earlier, taken on a smartphone. It's cheating a little bit. This was my iPhone hooked up to the 6-inch refractor telescope. So, a really nice telescope, pretty decent camera, you're gonna get a good image. But even still, like, the only real glitch we have, or processing error, it's not even a processing error, it's an optical error, because you're basically hooking the iPhone up to a eyepiece and laying over it on top and looking through, you get some blue hues here from like chromatic aberration from the lenses themselves. But otherwise, it's a really nice image that we got out of that scope. So if you have a scope at home, you could try hooking your smartphone up to it. They make nice adapters for that. But also handheld. Here's that telescope I was talking about. This is our 6-inch refractor telescope. And it's a super powerful magnification. So we do great stuff with terrestrial objects. The image of Saturn and Jupiter was through this scope. But I have my phone pointing out the window of the dome to show you the total lunar eclipse there in the sky amongst a star field. So on your smartphone, when it comes to imaging stars and the Milky Way, you want to make sure you're using a feature called night mode. Usually it activates automatically, but there are ways to improve its settings. And if you have a tripod, that's another great tool, because you can crank night mode up on modern smartphones. On iPhone, it's 30 seconds. Android devices have some incredible astrophotography modes I recommend that take really great pictures of the sky. All right, so as we close out here, I do want to mention, while Kopernik does not have our regular Friday programs for the remaining of winter here, we will start back up regular Fridays every Friday in March. But we do have one more event this winter season, and that is our Winter Star Party. Not on a Friday, it's on a Saturday. So February 21st, starting at 6 p.m. All right. And I always end with clear skies. Now, we won't really have that over in the coming days, so I will say please be safe with these snowstorms coming through. And those on the live stream, if anyone south of us too, it's like millions of people are going to be affected by this storm. It's pretty crazy. But
if you have a question, just raise your hand so I can take the mic so that the people on the live stream can hear the question. So, any questions? Wow, you answered them already. We do have a question. Oh,
What's the latest and greatest? No, I don't need that.
well, for the live stream.
Is Pluto a planet or not? It keeps changing.
oh, wonderful. That's a good question. And the basic idea, the way I frame this, Pluto is a planet. It's not classified as one of the primary eight. It's a dwarf planet, Jupiter that we saw earlier, if those weren't orbiting Jupiter, they would be planets. Callisto is bigger than Mercury, which is the moon of Jupiter. So in the end, it's semantics, and just we have to categorize things somehow. But Pluto's fascinating, Eris is fascinating, moons of Jupiter and Saturn all fascinating. When New Horizons flew by Pluto in 2015, I was following that since I was a kid. I read about it in a National Geographic Kids, I think in like fifth grade, when they were sending the spacecraft out in 2005, I think. And I was so amazed, like, that they were doing this thing, and I followed it in 2015. There was Pluto with this big old heart on it. It was amazing. That's like the first geological feature that came out, is Pluto has a big heart.
So, my view of the Pluto thing is that if you called it something else, call it Aldon, nobody would care. But because it has the same name as that cute Disney character, all of a sudden people are all up in arms. That we demoted it. But you had another question.
Yeah, the other one, I know all the planets are rotating around the sun. The sun is rotating on its axis?
It does spin, yes.
Okay.
It does.
Any other questions? All right. Oh,
So, how do you find the vernal equinox, like the 0 hour right ascension? Just looking at the sky, I'm not really sure.
All right. So with this coordinate system, we're basically just creating this definition based on the ecliptic. We have the ecliptic mapped out, and that's something you can do in Stellarium. That's one recommendation I would make, is to throw the ecliptic up in the sky, and also throw the celestial equator up in the sky, because it's the intersection of those two. And while the sun right now would not be on that section of the ecliptic and of the celestial equator, sky apps will mark that out in the coordinate field. That's the thing, like, it's not so much you're talking compass directions at this point, you're talking about a set coordinate system that you make definitions for, astronomical definitions, but not compass definitions.
Jenny, I think your mic may have moved down here. If you want, why don't you just grab this?
Okay, that works. All right. Any other questions? Oh, Mark has one. Oh, let's do this one here first, and then we'll get to Mark.
Yeah, thanks for doing this here for all of us. I really appreciate it. And where can you recommend somewhere to buy a great brand of telescopes to do things like this, to peer out into deep space?
So I have two basic recommendations. If you're looking to make some observations, just general observations, you want to point a telescope to a part in the sky and just see what's there, kind of like you would use binoculars by just looking around, I recommend a Dobsonian. That's Dobsonian. And it's a special kind of telescope that's pretty cheap, and you can get pretty large Dobsonians at lower cost. And they're light collectors. They're big light buckets. You can see a lot with them, but you need to know where things are and use sky apps to help you do that. Yeah, like Sky Safari. That's if you want to just kind of look around, and that's a great place to start. Just see what's out there. The other one that we are really we can't speak highly enough about right now is called the Sea Star, and that's SEESTAR, and that telescope is an all-in-one. It's not for visual. It's for some light astrophotography. And in a similar way with the Dobsonian, the app will guide you towards specific objects. The telescope itself is automated, so it finds stuff for you. And it's super easy to set up, and you get some amazing pictures out of it. There's different kinds of sea stars. There's the S30. Now there's an S30 Pro and an S50. The S30 is a wider field, so for bigger objects. The S50 is a narrower field, so zooming in a little bit more compared to the S30. And we're always happy to answer any questions about this too over email as you start to explore. Use info@copernic.org, and we can also guide you there.
So I intern at a school in the city. So how far do kids actually come and do events and programs here?
So we have our local school districts coming up pretty frequently nowadays. And we have some field trips coming up in February and in March from our local area. We also do on-the-road events. You may not have seen it tonight, but out in the parking lot there, we have our STEM van, and we take things like our portable planetarium in the van. We do some great exploring across our region. So yeah, there's lots we can do, and lots we do even.
We've taken it to New York City. Well, not the van, but we've gone to New York City. We've gone up to Plattsburgh. We've gone down to Philadelphia. So as long as there's a gas station somewhere near, we can get to you.
Yeah, exactly.
So they could make trips up here.
Yeah, definitely. All right. Any other questions? We had Mark in the back.
I was just curious, how many people here have a telescope?
Oh, the question was, how many have a telescope? Raise your hand. Awesome. All right, great. You want to buy one? Yeah. So, yeah, one recommendation we make, if you are not sure how to use your telescope, definitely come up on a Friday night, and our Kopernik Astronomical Society members, including Mark there, and Doc and Andrew, they can help you learn how to use your telescope under our dark skies. So that can be really powerful. Oh, we got a couple more.
You were talking about retrograde motion of planets. Does that mean the planet is traveling east in the sky, or relative?
You're going to catch me on one. My retrograde knowledge is not as good. But yes, it appears in the sky to go the opposite direction. That's the way it should. And that's because we're passing by. Yep. Oh, yeah. That question was about retrograde motion. And yeah, the idea is that it's switching its apparent direction in the sky because we're passing by it. And that's the effect. Any other questions? Oh, we got one in the back.
My question is, how does the sun turn and why does the sun turn?
Why does it spin? Yeah. Or yeah.
Talking about it spinning on its axis.
Yeah, that's a great question. So just like our planets in the solar system, as stars form, usually there's all this gravity pulling around, pulling this matter and squeezing it down, and the process starts some angular momentum. And in general, it's actually a pretty hard question to answer, but the stars are orbiting things, the planets are orbiting things, and as things form, they will start to spin. And things keep spinning in space, no matter what. There's nothing to stop them, so it just keeps on spinning forever and ever and ever, which is pretty cool to think about. So that's why the Earth is just going to keep on spinning too, at least over millions of years, at its current rate, more or less.
So again, if you have any other questions, Jenny will be here for a little while. But also, we have members of our Kopernik Astronomical Society, the astronomy club that operates out of here. We have the 6-inch open. And what are we looking at?
Yeah, so we'll do, me and Andy here, it's very, very, very cold. So we're going to take groups, and a small group will
And also restrooms are down the hall to the right.
So if you want to wait out in the lobby, we'll be taking groups after.
All right. Well, thank you very much, Jenny. Again, great presentation as always. And we hope, hopefully, we'll see you here for our Winter Star Party, and then starting in on March. Every Friday night will be open, regardless of weather. But hopefully, we'll have another slew of great viewing opportunities. So, thanks again.